go here. Let's go from the beginning. Okay. Welcome, everybody. Thanks for joining us today. Today, we're going to talk a bit about net zero renovations, and some of which is kind of specific to Indigenous and Northern communities, some of which is a bit more general because it's a pretty challenging topic. There's definitely some opportunities from perspective of energy savings and other improvements we can make to buildings, but there's a lot of challenges too, and we're not going to like sugarcoat this. We're try and keep it real and talk about those challenges too, and cost being one of them for sure. So when we talk about net zero in general, what are we talking about? Usually we're talking about net zero energy, although now we're starting to hear more about net zero carbon and some other sort of ways to think about it. But for now, I think we're just going to talk about net zero energy, which is a building that can generate as much energy using renewable sources as it uses on an annual basis. So if you think about what is essentially a self-sustained building, that's quite a bit different than being off-grid, because we don't need to generate the energy as we're using it. Typically in any kind of grid-tied environment, most of our communities are tied to the grid, and as long as we can on an annual basis generate as much energy as we use in our buildings, then we can be considered net zero energy. There's several certification programs that are available out there. The two main ones are through the Canadian Home Builders Association. We'll talk a bit about some of the materials that they've put out, and also through NRCan's EnerGuide labeling system. The Canadian Home Builders have introduced the concept of net zero ready renovations. So it's a little more defined, and they've also sort of allowed for what is essentially a net zero ready program for renovations, which is a building that's capable of generating as much energy using renewables on an annual basis, but the generation equipment is not necessarily installed yet. So you can kind of picture it as like step one of a two-step process of getting the building ready for being net zero without having all that solar or other power generation system in place. So what are some of the challenges in achieving net zero? So we have to remember that achieving a net zero building includes both a demand side, so what we require, and also the supply side, what we generate on site. So in the north, the further north we go, the more difficult achieving net zero can be in general, and renovations are no exception to that. And there's a couple reasons for that. As we go into colder and colder climates, we have increased heating energy demands. So just based on the number of heating degree days, we'll talk a bit more about that. There's fewer tools available in our tool belt to reduce energy demand. We'll talk a bit more about that. The fact that in the north we typically have more compact house designs actually makes it a bit more challenging to reach some of the certification definitions and goals. There tends to be a decreased potential for solar energy generation as the further north we go. And sometimes we run into, in a lot of, especially far north communities, electrical grid limitations that really make this difficult. We'll dive a little bit deeper into each of these. So usually when we talk about heating energy demands, one of the ways that we define that is using a term called heating degree days. And this is laid out in the building code. Every major community in the country is listed, and it's the heating degree days for each of those is listed in the code. Here's just some examples. Let me turn on my, whoops, I'm gonna go back one. I'm just gonna turn on my little laser pointer. There we go. So, for example, in the National Building Code, it's broken down into these 6 climate zones, zone 4 through 8. An example of a city in zone 4 would be Victoria, which is pretty much the warmest part of Canada, with 2,800 heating degree days. As we move up, we won't talk about all of these, but let's say Edmonton in 7A at 5,120 heating degree days. That tells us how much energy, extra energy is required to heat the same house in Edmonton versus Victoria. And of course, as we move into the far north and into the Arctic, somewhere like a Iqaluit with almost 10,000 heating degree days really starts to show the challenge from a energy perspective of meeting a net zero energy goal compared to Victoria or even Toronto. Another important thing to look at when we're looking at these climate zones in the National Building Code is that zone 8 is defined as greater than 7,000 heating degree days. And we know that, we can see Iqaluit's at 10,000. I work often in Cambridge Bay, which is at about 12,000 heating degree days. So there's a lot of gradations even within zone 8 where it might be possible to do in a lower zone 8, but not possible in the far north. So we also have, in some cases, fewer tools that are available to reduce energy demand as we go further and further north. And the biggest example of that is air source heat pumps. And we will talk a bit more about some of the specifics of that. But in the southern areas of Canada, air source heat pumps are being used to significantly reduce heating energy requirements because an air source heat pump can be up to 3.5 times more efficient than electric baseboard heating or even gas or propane furnace. We can really make some significant gains. And as we talk about some of the examples and some of the prototypes that have been done so far on net zero renos, you'll see that it's almost required to use air source heat pumps or some other type of heat pump technology to get there. The problem is that in many northern communities, air source heat pumps are really not an option due to how cold it is and for how long during the winter. And so as we could see, even with a new sort of technology, cold climate heat pumps, as we get into these colder temperatures at about minus 25, they're about 150% efficient, but then just aren't effective at all.
Sorry,
colder
Trevor.
than minus 25. Yeah.
Yes, I don't know what's happening with the mic, but it's muffling out once in a while.
Oh, is it? Maybe if it's a bandwidth thing, maybe I'll shut my camera off. You don't really need to see me. So let's see if that works better now.
Yeah.
Okay. And so basically, if you live in a community that has a significant number of hours of the winter below minus 25, then an air source heat pump all of a sudden becomes, not really a viable solution. And we'll talk a little bit more about that as we go. Another challenge is just compact house designs, especially with some of the definitions that are used for net zero energy. Certain size homes and certain layouts, like for example, a 2,500 square foot 2-story has about 5,065 square feet of enclosure or walls and roof and floor combined, which is a enclosure to floor ratio of about 2:1. So there's a lot of volume inside the building for not so much exterior envelope where we lose heat. But once we start to look at smaller buildings, for example, a 1,200 square foot bungalow has 3,600 square feet of enclosure, which is about a 3:1 enclosure to floor ratio. So there's a lot more wall and roof to how much enclosure we have, which starts to make the math a little more difficult in trying per square foot.
Okay, that didn't
And
help.
then
I'm
also
not sure what
finally,
it is. Sorry, Trevor.
oh
I'm
no,
not sure.
that's okay. Can everyone else, is everyone else hearing the same thing? Like Claude, you hearing bad, broken up audio?
Yeah, it's intermittent.
It's intermittent. I don't know what else I can do about that. I apologize.
It's a bandwidth
That's on
issue.
my end. Because I do webinars like this pretty much once a week, and I've never had that problem before. Is there, does anyone have any
Yeah,
other
somebody's
ideas?
typing in the
Okay, maybe someone's had a solution to this before. Uh, duh, 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 duh. Is it worth just keep going right now, or should we try and figure out a solution?
The only option would be for someone else to share your slides so you are not lowering the buffering issue, but maybe it will go away since you don't have it normal.
Yeah, I've never had this problem before. Too bad.
Yeah, Trevor,
Okay.
I think
Yep.
when it's processing your audio and your screen all at the same time, I think if the image stays on the screen and you just speak, it might not be a problem. It's when everything is moving, I think it's got a problem.
It's like maybe when it changes.
Yeah, because right now you've been clear for the last 2 minutes.
Oh, of
Yes.
course. Of course.
Yes.
Okay, well, let's keep going. I guess we don't have too much of a choice as long as you think that we're still providing value here.
Oh yeah.
Okay. So the point of this slide, as we're looking at it here, and maybe I'll even turn off this thing just in case it's part of the problem. Oh, I don't know how to now. Okay. That in a place like Iqaluit, so in the far north, we have really long summer days, and we can actually generate quite a bit of energy during those long summer days. But that's not when we need the energy. When we need the energy is in those coldest, darkest days of the winter. And so there's a difference between when we can generate the power and when we need it. And so now we start getting into things like batteries and other storage devices. And if you have a big enough grid and you have other sources and uses of energy, then that could be useful to spread those out over the year. But in a small community like Iqaluit, with a sort of a standalone grid, generating extra power in the summer doesn't help us. It'll just be lost essentially, and we can't just use it later when we need it unless we have some really expensive battery powered or battery banks, and that's not really a realistic approach right now. And yeah, also just the grid itself, depending on our community, if we're trying to switch some of our heating load from propane, natural gas, or let's say a diesel fuel of heat, and switch that to electric, we may not have the grid capacity to even do that. Depending on how the grid's set up in the community and how much extra generation there is, it may not even be an option. And in pretty most of the communities in the far north, switching heating load from diesel, on-site diesel burning boilers to air source heat pumps or some other electric system is not really possible. So that's a real limitation for us. So now that we know some of the challenges, I'm going to go through some of the interesting things that the Canadian home builders have put out regarding net zero energy renovations. And the one thing I found interesting was the ideal candidate house checklist. So there's 9 characteristics that can sort of help determine whether the building the house you have is a good candidate for a net zero energy renovation. So the first one that I talk about is pre-1980s construction. So if they're looking at, if it's worth making the changes, if in the buildings built before the 80s had much lower levels of insulation or using much more energy for heating. And so if you have an older building before the 1980s, that might be a good candidate. Another one is simple house shape. The more complicated the roof lines and the wall systems are, the more complicated, more difficult it's going to be to do a deep energy retrofit like this. This one's interesting. Old exterior wall finishes. If you're thinking about replacing cladding, siding, or brick anyways, then this is a really good opportunity to add exterior insulation. We'll talk a bit about some of those strategies, but it makes sense to me that if you have a building or a home that is getting ready to have siding replaced, that's a great opportunity. Simple roof shape, similarly to the simple house shape, is just makes it a lot easier to add insulation, to add ventilation if needed. Good solar aspect. So that's the other part of this, right, is the solar generation side. So if you have a lot of roof area facing south, then that's a good candidate because that's where we're going to want to put our solar panels, and we can get a larger array up there. We'll talk a bit more about that. Adequate space around the building for work, right? If you're, I work in Toronto sometimes, some of the houses are about 3 feet apart from each other. It's really hard to get equipment in there. Even ladders sometimes can be difficult to get in to do any major renovation work from the outside. So access is really important. A building that hasn't had any recent major upgrades, which makes sense. Below deferred maintenance, I guess that's similar to, needing old wall finishes. There's a bunch of work that needs to be done, whether it's painting or replacing trims or sidings. If that's the case, this is a good opportunity to also add insulation. And few or no observable hazards, things like asbestos and other types of materials that we now know we don't like to work with. So just I think a kind of a useful start if you're thinking about doing a net zero renovation, to see if your house is a good candidate. Now I'm going to go through a couple of different examples that are the Canadian home builders have put on their website as examples of when some of their clients have been able to do fully certified net zero renovations. So the first one, it's in a warmer climate zone 6, so that's like Southern Ontario. And they were able to bring basically their before renovation at about 92 gigajoules down to about 63. So a pretty significant drop, but not humongous. One of the things I noticed right away, and it's hard to tell from these photos, but they ended up completely replacing the brick on this building to get the walls to where they wanted it to get the insulation they needed, which is a pretty major and significant renovation, especially if the brick was in good shape and didn't need to be replaced. A few of the details for this, windows, and you'll see this is very consistent in the examples, triple glazed, U value of about 1.2 solar heat gain, low solar heat gain about 0.23. The walls that we talked about, they have R24 blown in bats plus R5 exterior EPS insulation. In the ceiling, R70 blown in attic insulation. That's not a big deal. That's not too bad or too difficult to do. For the foundation, so their basement, 5 inches of closed cell spray foam between offset framing. So that's about R25 of spray foam in the basement. So, not huge changes to the envelope, but pretty significant, about 34% better than the reference house, which is code compliant. Another thing though, and this is a big one you'll see throughout the examples, is air tightness. Getting the air tightness from 2.96 air changes per hour at 50 pascals to 0.8. That's very significant. There's a lot of heat loss that happens through air leakage, and making that building significantly more airtight is a big part of that. We talked about before, so the mechanical systems, and again, this is really consistent. Air source heat pumps. This one actually happens to have a natural gas backup and natural gas boiler for water heating, but that air source heat pump is a big part of that renovation to where they needed to go. And even at this, so it doesn't have really high levels of insulation, but because of that, they need a lot of solar, 16.3 kilowatts PV array. I did a little bit of generalization. This is what I added here. That's about 41 solar panels, which requires about 720 square feet of roof, which is huge. And the cost of that is going to be in the area of about $53,000 just for that renewable system. And this is the part, that's a lot. And that really kind of stood out to me. And the other thing that stood out to me on this one in particular, on the bottom left, you'll see because of these changes, they're now saving $310 per year on energy bills. I expected a lot more than that, but this is what this particular example showed. Again, that's in Southern Ontario. I'm going to give another quick example. This one is in Edmonton, so a much colder climate zone 7A. You can see the before renovation pictures. This building is pretty much ready to be gutted, so pretty good candidate in that way. And after renovation, it looks a lot different. There are a lot of renovations that occurred to this, not just building enclosure. But we'll look at what some of those are. In this case, they really did improve the building enclosure significantly. Again, triple glazed, dual low E and argon windows. It's a very standard approach. Walls are R14 plus R36 exterior reclaimed foam. So that's really significant. That's a very thick layer. Without doing all the math on that, it's upwards of 8 inches of exterior insulation. The ceiling, R50 spray foam in the flat areas, which is a lot. Again, that's about 10 inches of spray foam almost. And R77 blown in the attics. The foundation, R36, again, a reclaimed foam. So again, that's probably about something like 10 inches of foam. And they made some major changes to the envelope. Now 72% improvement over the reference house. Again, air tightness went from 4.24 to 0.74, real significant improvement in air tightness to get there. So in this example, they really went all out on the building enclosure. This is a colder environment, and they kind of needed to. They still went all electric with their air source heat pump and electric heat pump water heating to get there. And even at that, with going as far as they did on the building enclosure, they still needed a 12 kilowatt PV solar array, which is about 30 solar panels, requires about 525 square feet and about $40,000 worth of solar panels. So really significant. So just a couple of interesting examples there put out by the Canadian home builders. A couple things that have changed in the definition of net zero ready, which is actually a little bit helpful. The Canadian home builders, for example, will certify smaller homes based on energy use targets without requiring the matching on-site power generation. So to get to that net zero ready gets a little bit easier. So for houses under 300 square meters, between 345 square meters, need a reduction in heating, cooling, and hot water of about 60%. And for smaller buildings under 300, about a 55% improvement is required. And so you don't have to necessarily be able to match that with your solar panels in order to get this net zero ready certification. So this now makes net zero ready a bit more practical to achieve, and you can still receive the financial incentives when retrofitting houses in northern communities using some of these new definitions. It's kind of more helpful. I'm just going to give you another, this is more of a theoretical example because this is one we worked through in an energy modeling setting. In this case, we wanted to look at an energy modeling case study of a theoretical 2000s era house, less than 300 square meters in Iqaluit. The model of the existing house showed heating, ventilation, and water heating use of about 24,000 kilowatt hours per year. And then the reference house, which means that same house built to 2024 codes, it modeled at about 21,800 kilowatt hours per year. And so that's the number we need to reduce in order to meet the standard of that net zero ready program. And so that means we need to reduce our energy use to about 9,800 kilowatt hours per year. And so we ran through a whole bunch of different scenarios and different ways to get there. And this is just one example. And I just wanted to show this table to show how we got there and what percentage of the reductions come from different things. In this case, we have very high performing R44 walls, which produces a reduction of about 20%. So that's the most significant one. The improved windows made about a 2% difference. Again, that's about a triple glazed low E argon window. The roof and the floor system, in this case, we have an insulated floor system, but to upgrade those to R52, each made an 11% improvement. In this case, we did an improvement in air tightness from 3 air changes per hour to 1.5. And that made almost a 10% difference. So now we're starting to get there. We added, just to add a little bit of improvement to our hot water heating, we added a hot water tank insulation, which made about a 1% improvement. And then even in this case, to get better than 55%, we need to add air source heat pumps. And in this case, it wouldn't be the main heating source, but it would be a heating source in the shoulder seasons, in the fall, in the spring, in order to get us
Follow this FNNBOA
farther
Zero
to
Renovations.
55%.
It's like whew, over
Oh.
my head.
Rosemary, I can hear you. Sorry, if you
I'm
can
sorry.
mute yourself. That's okay. You probably didn't know. Okay, so that's just another example of how we get there. And you can tell it's especially in the far north, it's not easy to get there at all. It takes a lot of big improvements to the building enclosure, to air tightness, and still some significant mechanical upgrades to get to that net zero ready certification level. But I think there's a lot of things that we can learn from this, even if we start doing projects that don't necessarily meet net zero or net zero ready. There's a lot of things we can learn from the process on ways we can reduce energy use and improve our buildings. And so I'm going to go through now a series of improvements and different ways to get there. These are a little bit more general, but I think depending on where you live and your climate and what your energy goals are, these can be used to make significant improvements. So the first one is upgrading wall insulation. So there's a couple ways we can upgrade wall insulation. Most of the examples we saw, I think, before included adding insulation to the exterior, but we could also add insulation to the interior. And there's two ways to do that. We could do that by adding a layer of rigid insulation on the interior to give us that extra insulation value. When we do that, we also have the opportunity to improve our air barrier system on the wall that exists. So it's probably that layer of poly on the inside. We can inspect it and improve it and put a new one in if we want to improve air tightness at the same time. Really quickly, the steps that would be required to do this would be removing interior finish, so removing drywall essentially, installing a new or repairing the air vapor barrier that exists, installing that rigid insulation layer, installing new strapping, and then installing a new interior finish. And so some of the we'll talk about some of the benefits of working from the interior, but there's also another way we can do this, and we've seen in various examples over the years, and that's basically to build a new stud wall interior to the existing one, and using bad insulation to fill that space. And so in this case, it's a very similar approach in that we're going to remove the interior finishes. We're going to install a new air barrier, or at least repair and improve the existing air vapor barrier that's there. And we're then going to install a new interior stud wall, new bad insulation inside that stud wall, and a new drywall inside, or interior finish inside of that. So both two different ways of getting more insulation on the interior. Some of the benefits of working from the interior is that it's going to reduce thermal bridging, because we won't have the studs passing all the way through our insulation layer. We're going to have an opportunity to add a new, or at least repair that interior air barrier, which is a good thing for our air tightness, which we'll talk more about. We can retain the original exterior siding or cladding or brick or whatever we have on the outside. We can retain that. This new cavity we create, especially in that double stud wall, we can use that to run mechanicals. If we want to run electrical or plumbing in those walls, that gives us the opportunity to do that. And all the work occurs from the interior, which is good from an access perspective and getting work done. Although there are some challenges with that. When we add insulation to the interior, we still have that risk for air leakage condensation. And we'll talk about how exterior insulation reduces that. The challenge of replacing interior finishes, right? So obviously you're going to have to move a family out to be able to rip out all the drywall and replace all those interior finishes and all the work that goes with that. We end up losing floor space depending on how thick that interior layer of insulation is. And the other challenge is we're relying on the existing water control layer on the outside, which if it's in good shape, great. But if it's not, that could be a problem if there's still water getting in from the outside. And then, yeah, the home has to be unoccupied for this. So what's the other option for upgrading wall insulation? That's adding exterior insulation. Typically, we do that by adding rigid insulation to the outside. It gives us an opportunity to improve the air and water barrier on the outside, which is a good thing. And so what are some of the steps that would be required for that? In this case, we'd need to remove exterior cladding or siding. We'd need to install a new air water barrier, so house wrap or Tyvek. So that should be exterior rigid insulation out here. Install strapping and the new cladding. So some of the benefits of doing this are that we get to add that new water barrier, a new air barrier on the outside, which is great for building durability in the long run. We reduce the risk of condensation in our walls by adding insulation to the exterior, which is a big benefit if we're worried about mold and condensation issues. We're eliminating or really minimizing the thermal bridging through our structure, and all the work can happen from the exterior, which can be a good thing in that the home can be occupied while you do the work, but also can be challenging because access can be a problem. You need obviously more ladders and scaffolding and lifting devices and other things to make that happen. And of course, the other one is that now we're replacing our siding or our cladding, which can be an expensive part of the process. Also important to note, if we're adding foam board insulation on the outside, that we need to make sure we meet the insulation ratios that are called out in the NBC 925.52. Depending on what climate zone you're in, you may have to add more insulation on the outside to get to the insulation ratios that are required. Again, that depends on the climate zone you're in. What about upgrading roof insulation? If you have an open attic, that's really easy, right? We kind of talked about the blown-in insulation. Most of our buildings, probably outside of the Arctic anyways, have open attics. And so there's typically quite a bit of room there to add blown-in insulation. We also, though, while we do that, we want to take that opportunity to improve the air barrier system that is at the ceiling level in our homes. And that can be a bit challenging. And it may involve removing or relocating the existing attic insulation before we add any more, so that we can access that air barrier, repair it, improve it, seal penetrations that are going through the air barrier where there's plumbing or pot lights or other electrical penetrations. We can also, it gives us the opportunity to add any attic ventilation if required. So we'll definitely want to analyze how much ventilation is there and if it's adequate, if it meets the existing building code, and add ventilation if necessary before we do that. And then finally, putting in the blown-in insulation is the easiest part. Blown-in insulation is pretty cheap and quick and can be done with the building being occupied. So that's a good benefit for that. Some of the benefits, yeah, cheap and easy. All work is from inside the attic, so the home can be occupied. Some of the challenges is that we're going to want to perform air sealing of the ceiling plane first. And we're always going to want to review and, if necessary, improve attic ventilation. If we have a compact roof, so if we have a vaulted ceiling, we kind of are now, it makes it a little more. Now we have to choose whether we're going to add insulation to the interior or the exterior, similar to the wall systems. As you can see in this example, we used the interior insulated wall in conjunction with the interior insulated compact roof, which makes a lot of sense in a lot of cases. So it's the same process: remove existing interior finishes, install a new air vapor barrier or repair the one that's there, add new rigid insulation to the interior, new strapping, and a new drywall interior finish. And so again, we lose a little bit. Some of the challenges are that we lose a little bit of space in our buildings, but we're reducing the thermal bridging, which is a good thing, adding insulation. We have the opportunity to add a new air barrier if we want to, and can be really important, especially in a compact roof, to have a really good air barrier system. We don't have to put new roofing on. We can retain the original roofing if it's in good shape, which is good. And all work is from the interior. So again, good access from inside the building to do that work. Some of the challenges, though, are that we still have that sort of air leakage condensation risk. If any air does get from inside of our building into that compact roof, we could have condensation problems. We have to replace all of our interior finishes. Also, now we're relying on the water control and the quality of the existing roof on the outside, because we're not changing that. And the home will have to be unoccupied for this work because all that work's being done from the interior. And then similar to the walls, we have the option of doing adding exterior insulation to a compact roof. That would involve removing the existing roofing and shingles, installing a new air and water barrier, installing that new layer of rigid insulation, and then installing new strapping and either cross strapping or sheathing, depending on what kind of roofing we're going to put on there, and then install a whole new roofing system, either steel or shingles on top of that. So it's probably a more expensive approach, but if the new roofing is required anyways, it might be a good idea. Some of the benefits of this are we're getting a new air and water barrier, which is really good for the durability of our building. We're reducing the condensation risk in our roof because of that extra exterior insulation. We're minimizing thermal bridging, and all the work can be done from the exterior, so that home can be occupied during that work. The challenges are we're replacing all of the roofing. So we need basically putting a brand new roof on, which if it needs one anyways, might not be a bad thing, but is definitely a more expensive way to go. And access can be a challenge too, depending on the slope of the roof and access to the roof. From a construction standpoint, from a safety standpoint, could be more challenging. Upgrading windows. So we kind of talked most of the examples we used required that triple pane window with at least one, probably two low E coatings and argon to get to about that U1 or a little bit under in some cases. Just a note, so this is really a standard approach now, especially in all high performance northern housing, is the triple pane window. Just to note that there actually are higher performing options to that, including quad pane windows and windows that have suspended films between the panes that kind of act like, 4, 5, or 6 pane window. These are obviously very special and more expensive windows, but they're currently available, and depending on your energy goals, might be something to consider. Also, just to note, I'm not going to get into all this detail, but where it's really important when we are swapping out windows that we install them properly, and that where the windows meet the walls, that we maintain the thermal control layer, our water control layer, and our air control layers. And that takes some planning, and that takes some detailing. And this is just one example of a detail I put together for a client, and how much detail goes into that. We won't get into the specifics of that, except to say that these details are really important. We're going to also talk a bit about upgrading basement walls. Again, just like the above grade walls, we have the option of doing it from the outside or doing it from the inside. First, we're going to talk about adding insulation to the exterior of our foundation. Some of the steps that would be involved in that would be excavating the basement walls from the exterior, which is obviously a huge step and a major inconvenience to dig that all up. But if we want to go that way, we can do that. We can install, this gives us an opportunity to install new damp proofing and new rigid insulation and a new drainage mat to the outside, and to check and upgrade our footing drains. If we're having moisture problems in our basement, this might be the way to go to kind of add insulation and address moisture issues. Then we need to protect the above grade insulation, which is a bit challenging too. There's only a limited number of materials that can do that. Usually concrete board is the preferred approach, and then backfill. So that's a pretty major renovation unto itself because of the excavation and the mess that's going to make and the cost that's going to incur. But some of the benefits of the exterior insulation allows for new exterior water management details and systems. So if we do have water problems in the basement, this is one way to address them. At the same time, we're adding insulation. All the work is from the exterior, so the home can be occupied. It works well with that exterior above grade wall retrofit also. Obviously, the challenges are, the big one is the excavation and the cost of that and the mess and disruption of that. And that need to protect the above grade insulation is also challenging. It's an area that is always challenging in these projects because it's vulnerable to getting hit by, kicked or hit by whippersnippers or lawnmowers or that kind of thing and get damaged. We could also take the approach of adding interior insulation. And this is sort of a dramatic photo here, but the idea, this was the one photo I could find that showed both layers of insulation that I was interested in. Rigid insulation directly against the foundation wall, as well as a stud wall interior to that with more bad insulation. And so the steps that would be involved with that, assuming that there was no insulation on the interior of the basement wall, would be to install rigid foam board directly against the foundation wall. That can be done with adhesive. to tape and seal all the joints in that insulation, and then install a stud wall interior to that, and insulate that stud wall and install drywall. This is a really good approach from a moisture control standpoint, because that foam layer helps control interior vapor drive, which is an issue we see a lot of times in the climates where it's warm in the summer and cold in the winter. Some of the benefits of this approach are easier access from the interior, right? We don't have to dig up the whole exterior. Reduces condensation risk from the interior and exterior vapor drives. It's easier to achieve high R values because we're combining both that continuous foam board and that interior batt insulation, which is a bit cheaper to install. Some of the challenges being we don't have any access to improve the exterior water management, so we have to really be confident that we don't have any water issues in a basement before we put this much effort into it. And then, as with the rim joist, still needs separate detailing. And again, this is just another general detail that we need to think about, is that rim joist, the area where the floor system sits on top of the foundation wall. It's really important that we transition, our air and water control layers from the wall above to the foundation wall below. And there's, depending on which choices we make above and below, it might depend how we detail that rim joist area, but that's a really important area, especially when it comes to air tightness and condensation issues. We could also upgrade the basement slab insulation. We could either do that from above or below. If we do it from above, this allows us to use our existing slab as the structure. We don't have to take that out. We can use foam board, which can be sealed as an air barrier. This just requires us to put a new subfloor on top, which is usually plywood that can be tapconned or secured through the foam back down to the original structure. We can also do this from below the slab. If we were building a new house, that'd be the best way to go. But in this case, it would require the removal of the existing slab, which is really a messy, time-consuming process. The benefit of that, though, is that if we do that, we can add interior drainage tile. We can add a vapor barrier and radon barriers, and even plumbing at the same time, which could really help to modernize and improve the performance of our building, especially if there's water issues or potentially radon issues in the house. And again, a specific detail that's really important is the basement slab to basement wall detail, and that we have proper continuity of the insulation, the air barrier, and the vapor barrier through that transition. So again, just important to think through all those details, depending on what we decide to do. Just a little bit about improving air tightness. We've talked about air tightness a couple times along the way, and we really need to think about air tightness while we're performing the other aspects of the energy retrofit. And we want to think about adding or improving the air barrier components as we go, as we're improving the walls and the ceiling and the foundation. And air tightness is often a function of getting those details right. So those transitions, the wall to roof, the wall to foundation, the basement wall to slab, and the window installation details, getting those right is really critical to improving the air tightness. How do we improve the air tightness of our building? The only way to know is by measuring air tightness. And we do that with blower door testing. One question I often get is how airtight should the building be? Keeping in mind, we want it to be as airtight as possible. A really good goal, I think, for most projects is to get down to 1.5 air changes per hour, 50 pascals, which is what's currently called out for in the R2000 standard. It's also, interestingly now, was passed as a bylaw in Whitehorse. Every new building has to meet, every new residential building has to meet 1.5 air changes per hour. And so the builders there have quickly found out, figured out how to get to that level without doing anything extreme. Just again, about getting those details right. And then finally, we're going to talk a little about air source heat pumps. We're starting to run low on time, and we've talked a bit about them already, so we'll go kind of quickly through these. We can either get a central heat pump system and use ductwork, either existing ductwork or new ductwork we put in. We could also think about, in some cases, it might be better to use a ductless heat pump system where we have indoor heads in strategic places without any ductwork, just the line sets that run from the outdoor unit to the indoor unit. What are some reasons why you might want to choose a heat pump? The big one is energy savings. Depending on the climate and the heat pump choice, you could reduce heating energy by 50 to 70% just by going to air source heat pumps. You could reduce your carbon footprint depending on how clean your electrical grid is in your community and where you live. You can make a significant improvement in your carbon footprint. Also, potentially could save on heating costs. If you're replacing electric baseboards, you'll definitely save between 50 to 75% in your heating costs, which is huge. If you're replacing a natural gas or propane furnace, it might be less, might be break even on energy costs. The oil or propane, you may end up saving a little bit depending on what your current energy costs are. But certainly if you're heating with electric baseboards, it's a guaranteed major savings in energy. You'll also now get what I call free air conditioning. It's not free, obviously, but it's the same system you use to heat your house. You can now use to cool your house. So no additional equipment is needed to be installed to provide cooling for the summer months, which is a major benefit in some areas, especially with climate change and some areas of the country where we haven't needed air conditioning in the past, but are starting to now to keep our buildings cool enough so that we can stay in them year round. There's a few reasons why you might choose to not choose a heat pump. One is the climate factors. If the outdoor temperature spends a significant amount of time below -25, then you're going to need significant supplemental heat. So you'll need a whole other heating system, and the upfront cost may not be justified for a heat pump. If you live in a community with unreliable electric grid or electric grid that can't handle the shift from one heating source to electricity, then it might not be the good choice for you. If the service to your house or the size of your panel is insufficient, these are going to need to be upgraded. So that's a whole other cost that you need to consider, and you may choose not to use the heat pump. Electricity sources and costs. If you live in a province with an electrical grid emission factor greater than 100 gigajoules of carbon dioxide, we can talk about that. Then switching from heating fuel to heat pumps could actually result in greater CO2 emissions. So if you don't have a clean electrical grid, it probably doesn't make sense because you're just going to have a greater CO2 emissions. If you live in a community where electricity cost is greater than 3 or more times higher than the cost of heating fuel, then the total energy is going to end up being more expensive in the long run. So these are the things you need to keep in mind. And then also the technical support and upfront costs. So heat pumps are complex heating systems, require specialized skill for installation, commissioning, and maintenance. You need to have access to qualified refrigeration contractors and technicians, both for installation and maintenance and repairs. So that's really important. And depending on the upfront cost and access to contractors, it may not be worth the risk of having that system go down and not being able to repair it quickly. And then finally, in summary, we're have just about a few minutes for questions after this. a quick summary, right? So we tried not to sugarcoat this. As getting to net zero on a renovation is really difficult to do. Even in the best sort of definition of it, we need to achieve a 55% reduction in heating, ventilation, and hot water heating use. And that requires major improvements to the building enclosure, and typically also requires significant mechanical system upgrades, usually including air source heat pumps to get there. So although it may not be feasible or even possible to get to net zero for your project, for your community, there's still a lot of good principles to take away from this, and reducing our heating loads and different ways to do that in ways that are cost effective are really important, even if we can't get all the way to net zero. Now we'll just open it up. I haven't been keeping an eye on the chat, but I don't know if there's any questions in the chat yet, or
Yeah.
anyone that wants to unmute after that would be fine.
Yeah, hi, Trevor. I think John has a question. John, are you there?
I am. So Trevor, I guess the challenge is, well, we know that the blower doors are wonderful to identify, airflow and result in the mold. If a community is building several houses of the same plan, do they need to do a blower door for each house? Or could they just randomly do 1 and 5 and then just make the changes identified if it's the same contractors, the same process?
Yeah,
Are they able to do that?
If it's essentially the same design and the same contractors, I would recommend testing at least the first 2 houses to get a full understanding of what some of the weak points are in the air barrier system, and also to understand sort of what level they're getting to with the techniques and materials they're using. So I'd say at least the first 2, just as a learning exercise.
Okay.
If those 2 are coming out pretty consistently within the range you want them to be, then I think it'd be okay to not test everyone after that.
Right. And on the blower door, there's another association which we work with in Trevor as well, called Indigenous Clean Energy. They have lots of funds from NRCan to train First Nations to identify somebody to become like an energy auditor and do the blower door stuff. So I know they're always looking for community members to do that. So, right?
Yeah, right now the one of the problems with the system is that to become a certified energy auditor is really surprisingly long and complex process, and not a lot of people that would be good energy auditors can't pass the testing and the way it's laid out. So that's a challenge. What they are looking at doing right now is having sort of a certified, I don't know what they're calling it, but basically a certified energy tester as opposed to a full-on auditor that can run a blower door and get us this valuable information without having to know everything about energy and being able to do all the calculations and energy modeling and all that stuff. So they are working on that, but it's a bit of a challenge right now.
Yeah, that's a good point. Yeah, and I know this is not an Indigenous issue. It's even off reserve as well, correct? Like
absolutely.
It's just, they made it really complicated.
There's guys that have been doing energy audits and are really good at them for like 10, 15 years, and they can't pass this certification test because of the way it's done. It's really math heavy, and it's really a lot of memorization, and so people that can be good at their job just can't pass the certification test. It's pretty frustrating.
Right.
Yeah.
Wow. Trevor, sorry, go ahead.
Was that Bruno? Go ahead, Bruno.
Yeah. Well, I was just Trevor touched on modeling, and I'm wondering the decision making on if you're about to renovate, what to do how much wall insulation to add, what the window rating should be. And in the decision making, is it always necessary to go towards modeling and engaging an expert?
I think it's just, it depends what your goal is, but if your goal is just to make significant improvements, but you're not necessarily looking to get to net zero, then it's not, might not be important to do modeling, but it is kind of important just to understand the sort of relative changes that come with the different improvements. So that one chart I showed where improving your wall system can make a up 20% reduction, but improving your windows might only make a 2%. So it's just good to sort of have a bit of a feel for what different improvements will have on the overall energy use so that you can kind of decide where the best place to spend your money is.
Right. I guess I'm just thinking of a homeowner needing help and deciding what they should do. And there's so many combination permutation that you showed.
There
You know,
are
insulating
so
on the
many.
inside or the outside. There's got to be a way to help with in that decision making. And of course, there's costs associated with all of those. Yeah.
Yeah, for sure.
Go ahead, Trevor. Sorry.
No, that's okay. I was just agreeing that there's a lot to it.
Okay. A couple more questions. AL, 2 questions. First, there's a program. Is there a program for northern communities? Is first question.
So the programs come and go quite frequently. So there may be, I've never seen one specifically for northern communities, but they would all the other programs would apply. That being said, the programs come and go quite frequently, and you have to stay on top of, understanding where to even find out, because they'll only last like a year, a lot of them. So they do change quite frequently, and I'm not up to speed on all of them. John may have some more insight on that.
Yeah, good question. And we're in this, I think, bureaucratic budgetary flux right now. So nobody knows who's coming and going in terms of projects. The new Liberal under Carney hasn't really identified where they're going. I think the best source is really Indigenous clean energy. Talking with Corey, they would know because that's their mandate. So I would reach out to Indigenous clean energy. And when you reach out to Corey, ask if there's any money and then tell them that you need money. So give them like a 2-pronged question. Is there a project? And then say, if there is not a project, we'd be interested, because then that will help them to go after funding. But they would be the ones who will probably be best to do that.
Yeah, I think, John, you kind of answered the second part of Al's question about government funding. So thank you.
Yeah, so on the government funding, and again, Indigenous Clean Energy has been doing extremely well on getting support from various groups. I just thinking in Manitoba, Efficiency Manitoba actually has also put a lot of money into First Nations. So depending where you're at, I would actually go both federally and ask the province or territory, because they may have funds as well.
I have a comment here too, Trevor, and I don't know if you have an easy answer to it, but I'm looking at it. What about on the retraining and workforce skills side? I start looking at this is all fine and dandy, and certainly we know there are some challenges, but we almost need to rethink the way we basically not just build homes today, but also retraining if we want to look at rehabbing existing housing, because you've offered us a good overview of many ways that this process could be tackled, but it's almost like we have to rethink. It's just not the old wood frame house that it used to be.
Yeah, and certainly in renovations, there's so many, like you said, permutations and combinations of what exists and what you can do with what exists, that it's really complicated. Like at least if you're starting with a new home, like you kind of know what you're starting with. But when you're dealing with an existing home, there's so many factors. It's very complex. But certainly there's some groups working on trying to train the workforce to be able to do this, including the Canadian home builders and others that are kind of starting to focus now more on the skills required for renovating existing homes.
Yeah,
So it's-
I'm almost wondering if that is something we may want to consider collectively in FNNBOA. Well, we've been targeting, new construction and, all those areas. It is a huge gap of, well, there's a number of gaps, but one is the renovations and one is the building maintenance side, which we've been working with FNHPA. But I like the idea of maybe thinking of targeting the renovators and again, it's something we could try to flush out as something for this fiscal year coming out. I think it's a huge gap and I'm sure many on this call could talk about the frustrations of trying to do renovations, let alone getting people who knows what they're doing, because it's a tough, even tough off reserve. Again, this is not
Right.
Academy Award for First Nations, right?
Yeah.
It's on and off a challenge. Anyway, good point. Well done, Trevor, as usual.
Yeah.
Great. Thanks.
I can say I don't see any other questions, but if anybody wants to get their last chance in, please do.
Sounds, again, I just go back to the decision making, which you all touched on now. I guess the pressures on building new housing, more houses, as opposed to looking at improving what's existing. And there must be a way, a help for a decision tool in determining what's the best, how much should be contribute, how much should be the budget go to new housing and how much should go to renovating. There must be a way to help out in that decision making is what's needed, I think.
We actually developed a decision-making tool for FNNBOA, which makes to how to proceed in terms of, spending on this, spending on that. I could try to find that and send a link to everybody on this webinar. I remember we use it a lot and to help managers, especially housing managers, and to make decisions. And there's almost like a decision tree that we developed. Claude, remember we did that with?
Yeah, I think I think Bruno helped in the development of that one. It's in one of our booklets.
Bruno, that's when you worked at NRC.
Yeah,
we got funding from Dino. And I know we had a lot of clicks on it when I was just looking at it, so it's still downloaded a lot. But if you go into the FNNBOA website, I'll just do it quickly, FNNBOA, and it's part of a decision-making. Let me see if I can find it here.
It might be in booklet number 2 of the net zero.
okay.
Okay.
Yeah, so that's the sort of thing that needs to become a part of all this in the decision making, because it's overly complex for most communities, I would think, on what to decide on, and all the options that are available.
Yeah, because one of the examples that Trevor used earlier, that $53,000 for solar panels,
Yeah.
And the savings was $310 a year. And I'm looking at even over 20 years, that's not a lot of energy, like money saving, upfront costs. That was sort of like, boy, we're in energy debt on that house.
To be fair, the second example, which I didn't mention, they claimed $2,000 a year. So that's more what I was expecting to see.
Yeah. When I looked at that one, I jotted down the numbers and going, well,
Okay.
yeah, over 20 years, that's $2,000 a year at, for 40,000 of investment.
I know.
Yeah, the focus seems to be on those examples. It's mostly compliance with net zero ready than really a payback period. So it's
Definitely.
just the scope of what it takes to comply. Yeah.
Well, and I think, Trevor, in all fairness, you've presented both sides of the argument, because it certainly can be a benefit, but certainly at what cost?
Yeah, it's one of those things where technically we can do anything, but is it worth the price? Yeah.
Yeah.
Right.
So I actually found the link. It's similar to what we had for the net zero, but the one I've been thinking of is housing decision-making tool for chiefs and councils.
Oh,
And this was designed to focus on, asking varied questions in terms of using the houses versus prefabs. And so it's really fairly well done. And key questions: new construction, prefabs, how to do procurement, no procurement. So I put the link in below, and maybe something, Chloe, we could incorporate this and the net zero as part of the Dartmouth conversations on renovations as well. Just thinking out loud here. So
Sure.
anyway, there's a lot of great stuff. But the renovations is a gap for everybody.
Yep.
Yeah. So, all right.
Thanks again, Trevor.
No
Well
problem.
done.
No problem.
Very
right.
good.
Thanks, guys.
Okay, perfect.
Good.
So there's some links in the chat for anybody, but I'll also share it when I share the recording.
Yeah.
Perfect.
And we have one more webinar next week. Is that it?
That's correct.
Yeah. On architect drawings.
Oh, okay.
Okay.
Yeah. Thanks for reminding
So
me.
thanks everyone for participating, and excellent job, Trevor.
All right. Thanks.
Thanks,
Right.
guys.
That's good.
Bye.
Everyone have a great day.
You
Okay,
too.
take care.
Bye-bye.
Thanks.